What I want to talk to you about today is related with work that I have been doing together with Marcelo Pereira, a colleague at Heriot-Watt, and two of our PhD students, Luis Vargas and Matthew Holden. And the general area that I would like to talk to you about is the area of Bayesian inverse problems. And in particular, I'm thinking about imaging inverse problems. So I believe that Savas is talking after me, so he's also going to talk about some work that we're doing, that he has been doing this year in his first year of PhD. But yeah, so basically I'll talk about inverse problems and Bayesian inverse problems, tell you a bit about different ways that you try to incorporate prior information, and then also talk to you a bit about algorithms. So the talk has a little bit of everything. I'm going to try to go slow in the beginning. I mean, I don't know what the policy is in terms of questions or what the policy had been, but if you have any questions, please feel free to interrupt me either by just shouting or maybe writing something on the chat, and then Dimitris can ask the question for you. I have no way to know what is going on in the chat because I'm sharing my full screen. Okay.
Yeah, that's fine.
So here's a brief outline. So I'll spend the first like 10 minutes, if you like, setting up the scenes and what do I actually mean by an image inverse problem. Then talk to you about optimization versus sampling. These are sort of like two facets, if you like, of the same problem or of problems that they are related. And then, I mean, I think Dimitris, in his very kind introduction, mentioned the word numerical analysis a few times. I really think as a numerical analyst, or at least that's what I like to think about. So I'm going to talk to you about two computational devices, an ordinary differential equation and a stochastic differential equation that in some sense can be thought of as computational devices that allow us to solve the optimization and sampling problems. And then really the rest of the talk is essentially two talks put into once. There are two different routes that you can try to follow if you want when you're modeling imaging inverse problems. In the one, which is like the more traditional one, and it has been existing for the over 20 years, you sort of follow when it comes to modeling the prior. You use a function that you can write down by pen and paper, okay, and then. And that's sort of like I'm going to be talking maybe like 20 more minutes about that. And then very quickly, I'm going to tell you about some work that we have been doing in trying to incorporate directly the data into creating a prior for our imaging problem. And then I will just finish with some conclusions and future work. Okay. But let me just start. I mean, especially given that this is a student conference, in some sense, I just want to show you two very simple problems. They're very innocent problems, but they actually keep on appearing all the time, at least in my biased view, in kind of everything that you're trying to do in applied mathematics, okay? So the first one is optimization. Somebody's giving you a function pi of x in Rn, already typo number one. It's n there, it's d in the minimum, but that's fine. And you try to calculate the minimum of it, okay? So that's a very simple problem. Simultaneously, it's a very simple problem to state. It's actually a very difficult problem to solve in all generality. So you need to start putting some assumptions on pi. And this is basically what we're going to do implicitly in the rest of the talk. I'm not really going to be focusing too much on conditions on pi, but in general, this is a very difficult problem to solve. And then the other problem that is also very innocent looking relates with sampling. Essentially, somebody gives you a probability distribution with a smooth density pi of x, and you're asked to calculate some expectations with respect to that density pi, okay? And the big problem here, in some sense, is that the space that you are looking into integrating is quite high dimensional, so you couldn't do things like quadrature or anything like that. But I mean, the point is that these two problems are quite innocent looking. They're quite simple to state, but they really appear all the way through applied mathematics. Okay, and I'm just going to show you a particular instance of that in the case of the imaging inverse problems. So in the picture here, I have two images. Okay, on the right is the original image. Okay, or if you like, is the true image that you would like to take a picture of. But if you have shaky hands like me, you might end up getting the picture or the picture on the left. Okay. So what would you like to do is you would like to somehow be able to retrieve what the original image was without accounting for the shaking, if you like. Okay. And if we are to phrase that in mathematics, we are interested in basing in an unknown image x. Okay. But x is not what you are measuring. The data are not giving you x. They basically give you a version of x, okay, which we'll call y. These are the data. And they are related to x by a statistical model, okay? So pi of y given x is the probability of getting your data y, assuming that your true image was x, okay? And the problem here is two-facet, okay? I mean, even if you don't go into the statistical framework that I will go in just a second, there could be multiple x's, okay, that they can give you the same y because of the observation process. And even if that transformation, if you like, is invertible, is severely ill conditioned. Okay, so it's not so easy to say, okay, let's try to calculate the inverse of this statistical model or of this procedure and obtain our x. Okay, so the simplest model, and this is basically the model that I'm going to be studying today, is assuming that y is related with x by this linear relationship. Okay, so A is a matrix. Okay, which most of the times is rank deficient. Hence the whole point that I was saying, that even if you didn't have the noise w, you couldn't just invert A because of it being rank deficient. Okay, but that's basically what I mean by measuring y that's related to x by a statistical model. So later on we're gonna see, if we put a specific assumption on the noise, we will be able to write down explicitly the likelihood function, if you like, the probability of y given x. Okay, so how do we model now all these thing in the Bayesian framework? As I said, we don't have enough information just from this relationship to fully recover x, because of the problem being ill-posed. Okay, so what we're doing in the Bayesian framework is we are using priors to try to reduce uncertainty and deliver accurate results. So if you're more familiar with optimization approaches, the equivalent approach, or what a prior, if you like, is in the variational setting, is nothing else than what people call regularization. Okay, so we use a prior that incorporates information that we believe it's true for the random variable x. Okay, and then using a Bayes rule, we obtain the following equation. So P of x given y is the posterior distribution. Okay, and it models our knowledge about x after observing y. Before observing y, all our knowledge for x was incorporated in the prior. Now we have observed y, so if you like, we're updating our belief about x. And as I said, in this talk, we will consider two different approaches towards incorporating prior information. The first one, and as I said, that's sort of like the more traditional one, is to give a functional form in the prior of x. Okay, and for the problems that I'm gonna study here, that results into the posterior distribution having the following form. Okay, it can be written like the exponential of a function of minus a function phi. I mean, in principle, that's a function of x and y, but I have suppressed the dependence on y. But the important thing, and that's sort of like very useful in terms of algorithms, is that this function phi of x is a convex function, or a strongly convex function, and this would actually be quite helpful to us when it comes to designing algorithms. So that's the first approach. That's the traditional approach. Now, if you like, what the cool kids are doing these days, they're trying to incorporate machine learning in everything. Okay, so we will try to be cool ourselves as well and try to learn the prior from the available data. Okay, I'm not gonna talk more about this now, but we'll come back to this later in the talk. Okay, but if you like, within this framework, okay, sorry, within this framework of imaging image problems, I've told you about optimization and sampling. So let's see what does that mean in the context of Bayesian inverse problems. Okay, the predominant Bayesian approach in imaging is map estimation. So map stands for maximum is where the probability, is where the probability density gets maximized, okay? Again, it's just linked with the posterior distribution by this minimization problem, okay? So that's already the first instance of an optimization problem in this imaging inverse problem setting, okay? And the good thing, especially because we have assumed that phi has these nice properties of being convex, or it could be even better by being strongly convex, it can be computed efficiently, even in very, very high dimensions. I mean, there are a lot of very sophisticated algorithms now that allow you to calculate this problem very quickly. And when I say very high dimension, I mean, a normal image might have dimension 10,000. If we talk about like astronomical images, they might have dimension 100,000 or a million, okay? But in some sense, this kind of approach has some limitations and does not utilize the whole information that you have. I mean, if you think about it, you've done your Bayesian modeling and it gave you a probability distribution, a posterior distribution, and the only thing that you are doing is saying, okay, where is this probability being maximized, okay? But that's useful information, but it's not everything, yeah? I mean, it's like telling you, okay, I tell you something about here's a probability distribution, and you should just be satisfied by knowing what the mean of that probability distribution is, okay? So it has some limitations. As I said, it gives little information about the posterior. And then if you want to do some like things like model estimation or estimate uncertainty, this is not something that you can do by using this estimator. Okay. So, and in particular, there's a small experiment here that I want to discuss very quickly, just to explain why we might need more than just a map. Okay, so this on the left, these are the results of a microscopy experiment. Okay, it's a blurred image. You would like to unblur it, and this is what you see on the right as the Bayesian estimate. And what you're interested in identifying in this microscopy data set is where the molecules are. Okay, but on top of that, you would like to model not just where they are, but also how certain you are about where the molecules are. So in particular, you know, if you thought that this the position of those three highlighted molecule structure was important, you would like to know how certain you are that these three molecules are indeed there. Okay, and this is not something that you can do with a map estimator. Okay, this is something which requires the calculation of integrals with respect to the posterior, and hence take us to the sampling problem. Okay, so I hope I haven't gone too fast and I've explained a bit sort of like where the optimization and sampling comes into place in this context of Bayesian inverse problems. So before, I would like to finish my introduction by telling you a few things about the two computational devices that we're basically going to be using to utilize and find solutions to optimization and sampling problems. Okay, and the first computational device is just an ordinary differential equation, which I'm sure that most of you, if not all of you, are familiar with, and it's called the gradient flow. Okay, it's a very simple differential equation. So pi, again, is sort of like the function that we want to calculate the minimum of, okay, or a minimum of. In our particular case, for our posterior, I forgot to mention that because phi, we had like that pi of x given y was exponential to the minus phi, and phi was convex. That means that the minimizer, especially if it's strongly convex, it means that the minimizer is unique. Okay, so this equation here has the potential of giving you the minimizer of the function. And I mean, it's very easy to see that. You just differentiate your function pi of x along the trajectories of this equation. And what you basically see by just using simple chain rule is that pi reduces as a function of time. Okay. And if you assume that your pi was bounded from below, which would be according to the assumptions that we have, the only thing that can happen is for x as t goes to infinity to converge to a point for which the gradient of pi would be equal to 0. Let's call this point x star. and under the assumptions that we're studying, for example, in our models, that would imply that the solutions of this differential equation would converge to the unique minimizer of your posterior distribution, or the maximizer in this case, because there's a minus there. Okay, so this makes this equation, I mean, the gradient flow, central in terms of optimization purposes, or if you like, the simplest choice when it comes to designing optimization algorithms. And I'm going to come back to that in just a second. Okay, the other computational device that relates more with sampling, okay, is the following stochastic differential equation, which is called Langevin dynamics. Okay, I mean, it looks pretty similar to what we had here. Okay, the difference is that now you have a bit of noise here, some stochastic fluctuations. And what you can basically show is that under appropriate assumptions on log pi of x, one can show that the dynamics are ergodic with respect to pi of x. I mean, you might not know what dynamics being ergodic mean. I mean, there is a visualization here, but how is that useful in terms of what I started to do? Remember, we said that we would like to calculate expectations with respect to pi of x. Okay, but basically what you see here is that if you are to calculate a long time average of the solution of the stochastic differential equation, okay, that would actually converge to the quantity that you're interested in. And that's basically what I mean in terms of computational devices. The first device is a ordinary differential equation. If I run it for long enough, it would converge. If I would solve it analytically and run it to infinity, it would give me the minimizer of my function. Likewise, if I was able to solve this stochastic differential equation to infinity and calculate the special average, it would basically give me the quantity of interest. Okay, so in some sense, I'm done. Yeah, I mean, we can stop here and enjoy our break because we have the computational devices. If we're to assume that we were to solve them exactly and run them to infinity, then we will get our answers. And that's what I'm sort of like saying, having here as a slide in an ideal world. Okay, we would like, in terms of optimization, to go to infinity to reach the limiting behavior of the differential equation as quickly as possible in terms of function evaluations. And likewise, in the case of sampling, we would like to go to infinity as quickly as possible. And there is the additional catch, which I'll try to explain later on when we get to that. Once we go there, we want to produce samples that they are IID, random variables. Okay. However, the world is not ideal. Okay. Going to infinity as quickly as possible, like reaching this limiting behavior as quickly as possible, implies that you can take very big time steps in your numerical discretization. But reality will come back to bite you because if you have done sort of like any numerical experiments with ODEs, for example, you know that you cannot take your time step delta t being as large as you want. Okay. So what sort of like the first part of the talk is about, when we're going to be talking in the functional setting, is trying to understand this statement a bit more and see what we can do in terms of improving it. Okay. And two very simple algorithms that are based on discretizations of the gradient flow or the Euler-Maruyama equation are basically the ones that I have written here. There should be a gradient here. Sorry, I apologize. It's a gradient descent and the Euler-Maruyama. And they look quite similar. The only difference in the Euler-Maruyama case is that you have to add this fluctuation. Okay. So now, I mean, having finished with the introduction, let's just try to look at the first part of the talk where I'm going to be talking about functional priors. Okay. Remember, functional prior is when I write a specific form for the function for the prior on x. Okay. And let's just have a closer look at what these priors look like for computational imaging. Okay. So you would recover. So you have the posterior distribution. If you remember, the posterior distribution has a term that relates with the likelihood and has a term that relates with the prior. So G1 is a term that relates with the likelihood. And if you assume this linear model with Gaussian noise that I talked to you about, then this is just a very simple quadratic likelihood in X. Okay. However, when it comes to the prior distribution, it's very useful in terms of computational imaging, to use priors that they are not differentiable. So, for example, you might know that the values of x belong in a specific set. That's basically what this indicator function means. Or you might have some dictionary about how x is behaving, and that leads to terms of this form. And basically, the problem here, or the first problem here that appears here, is that, okay, in the previous slide here, I told you about two simple algorithms. They both involve the gradient of pi or the gradient of log pi. Okay, how, which in this case, the gradient of log pi is nothing else than the gradient of G1 plus the gradient of G2. But I mean, for most of the typical priors in computational imaging, G2 would not be, it would lead to posteriors in which G2 is not differentiable, okay? So it creates the following question: how can we make sense of gradient algorithm if the gradient doesn't exist, okay? So let's just try to do what I call the poor applied mathematicians approach, okay? I have background in applied mathematics. So, and let's just look this in a very simple case, in the case of the absolute value of x, okay? So the simplest thing that you could do, or at least the simplest thing that I could think of doing, is go near the singularity, go near the corner of go near zero, and where you have this kind of behavior, just smooth it a bit. Yeah, just replace this kink with a quadratic, and this is basically what you see here in the picture, and this is the way to do it, to describe it in terms of mathematics. So you have G2 of x, okay, it's non-differentiable, but what you're trying to do is to replace it with a differentiable function. So if you were to do the calculation here, you would see that G2 of lambda is differentiable. But this kind of sounds like a very poor approach. Yeah, I mean, this is like the simplest thing that you could think of. I mean, is that a sensible thing to do in practice? And could you do it in a sort of like systematic way? And this is where convex analysis comes to the rescue. The procedure that I described to you here, which just looked a bit arbitrary, I said, okay, let's just replace the kink with a bit of a quadratic, has a name in the convex analysis literature. Okay, it's what people call the Moreau-Yoshida envelope. So if you now have a function g that is not differentiable, and you consider this function g lambda of x given as the solution of this minimization problem, what you can prove is that A, and that's going to be important in terms of designing algorithms, that this function g lambda inherits the convexity properties of the original one, okay, but it's also differentiable with Lipschitz gradient, okay. So you can actually write down the gradient of g lambda, okay. It's Lipschitz continuous, and you with parameter lambda to the -1, and when it comes to calculate this prox, it relates again with an optimization problem. Okay, so and if you were to ask how g lambda of x looks for this specific example of absolute value of x, it would be nothing else than what I just described. So in some sense, the poor applied mathematicians approach kind of works, but you have convex analysis that allows you to formalize that a bit more. So now we have a function, we have something that is differentiable. G2 now becomes differentiable, so I can start designing algorithms because I have gradients. And this is basically what I have written down here. Okay, so you can write down. I mean, this is the celebrated proximal gradient iteration. Basically, I won't go too much into details about how this comes about, but basically it's just a splitting algorithm on the sort of like, if you're familiar with splitting algorithms on the normalized, not using G2 of lambda instead of G2 in the gradient flow. Okay, and what you can show is that this algorithm here has a favorable properties in terms of convergence to the map estimator. Okay. So, but the talk today is more about sampling. Okay, so let me look first of all at what is the effect of introducing this lambda the posterior distribution. So here are three examples in which, I mean, in the first and the third, the function was not differentiable, and we turn it into, the posterior was not differentiable, and we turn it to a differentiable posterior. What we basically see is that as lambda increases, we get a worse approximation to the posterior distribution, and that's not a surprise, okay? But so if you'd like to have like not introduce extra bias by introducing this lambda, this smoothing, you would need to take lambda to be very small. And here basically is you see what is called the Majula algorithm, which is nothing else than, sorry for flipping slides like this, is nothing else than the Euler-Maruyama, but now instead of applying that in G1 minus G2, because we don't have a gradient of G2, we replace G2 with G2 of lambda, and then apply, take the gradient of that, and that just leads you to this Majula algorithm. So this is basically, if you remember, it's just the gradient of G lambda 2, okay? And this is basically what you will get if you were to run a long chain of this Markov chain and bind things together, okay? So as you can see, it is sort of like, it gives you kind of a reasonable approximation to the true densities, okay? But already, as we said before, because lambda is not zero, you're introducing an error. In order to make this error small, you need to take lambda small. But the problem is that when you take lambda small, because of this term here, okay, delta t has to be small as well, okay? But remember, in order to be able to get anything reasonable, because of ergodicity, I need to integrate for quite a long time, okay? So in terms of obtaining samples from the posterior, I need to integrate for a long time. But on the other hand, in order to get something accurate from the posterior, I need to have lambda small. But that means that I need to use a small time step. So as I make my lambda smaller to get a more accurate approximation, I have to integrate for longer, okay? So that sort of like creates this conundrum that I've written down. The solution for this, and I'm not really going to go too much into detail about that, is to use some specific solvers for stochastic differential equations that basically have the following property. They only calculate things based on S gradient evaluations, okay, but they allow you to use a much larger time step than traditional explicit methods. And this is basically how the methods look like. I mean, it's not important. I mean, it would have been just a whole other talk trying to explain where these methods come from. The one thing that basically I want you to keep in mind, and this is really the key property of these methods, is this one here, that if I was to use, let's say, the Euler-Maruyama method and do S gradient evaluations and ask what is the largest amount of time that I could have traveled, it would have been S times lambda to the -1. But with these methods, I can travel, I mean, again, using S gradient evaluations, I can travel distances of S squared lambda to the -1. So for the same computational cost, I'm able to integrate much further into time, okay? Which kind of solves the problem that I said, as lambda partially solves the problem that as lambda becomes smaller, I have to take a smaller time step, okay? So I just want to describe the results in a tomography experiment, okay? So this is the original image. This is called this is the original image, yeah. And what you observe this image on the Fourier space. You observe some of the Fourier coefficients, and you have some noise on them. And what you see on the right is basically your observation on the space on the original space. So as you can see, I mean, it has some information from the original image, but it's not that great, okay? So what we would like to do, we would like to compare now the different algorithms and see which algorithm behaves better in some sense, okay? So I will basically compare SK-ROC with Majula and Mala. I haven't really told you what Mala is about, but I will explain that you can take Mala as being the absolute truth. So it's a way to solve, it's a very expensive way of obtaining exact answers about your posterior, okay? And as I said, you know, in the slide of sampling, I said you would like to go to infinity as quickly as possible, okay? And once you get to infinity, you would like to produce samples that are as much as possible to IID random variables, okay? So what you see here on the left is the convergence towards the typical set of the posterior distribution as a function of, as a number of function evaluations. And as you can see, out of the three methods that I have described here, SK-ROC is by far the one that converges the fastest, okay? So because essentially of what I told you, that you are allowed to take larger time steps for the same computational cost, that means that you get to infinity faster, okay? So it kind of like ticks the first box. It also ticks the second box, that once you are at infinity, how that you would like to produce samples that are as close as possible to IID, okay? A way to measure that is to look at the autocorrelation decay. And as you can see, very quickly, the SK-ROC gives you samples that are uncorrelated with each other, okay? So in some sense, it kind of ticks the second desired feature that I ask for a method. But on the other hand, something that I haven't really told you about is that none of those methods, so there is already bias because you replace pi with pi lambda, okay? But there is an additional bias because then you are not solving the stochastic differential equation exactly, you're doing a numerical approximation to that, okay? MALA, I mean, Metropolis adjusted Langevin algorithm has a way of removing those bias. So this yellow line here, you can think of it as being the absolute truth, okay? This is the correct behavior of pi lambda. But then both Mayula and SK-ROC have some error in them when there is the kind of equilibrium behavior. But what you see is that SK-ROC is kind of like closer to the truth than Mayula. Okay, so just to sort of like repeat what we've seen in the slides, because I think it's quite important. We've designed a method that is able to converge faster to the typical behavior. It's a method also that for which samples decorrelate quite fast, and also doesn't have that much bias as Mayula. So it's a very good method in a nutshell. And essentially, as I said, the main take-home message from here is that because it allows you to take bigger time steps, it has all these nice properties. Okay, so I mean there are a few more numerical results here, but I don't really wanna talk about them. I just wanna spend, I guess, Dimitri, I have 10 minutes or 5 minutes. How much do I have?
Minutes, perhaps even 15.
Okay, no, I'll try to finish. I'll try to finish in 10 minutes. I mean, just basically give you a flavor of the work that Matt has been doing on data-driven priors. Okay, so this is sort of like in the previous part of the talk, we just talked about you know, writing explicitly the prior. Now I want to sort of like learn the prior from data, okay? And what I mean, you know, if you think about the case of images, okay, we really have a lot of natural images out there, yeah. So you can think of all those images are samples from a distribution, okay. If you are able to learn this distribution, okay, and you have like a form for that distribution, then you would go into your base rule, and then you would have a different posterior like the one that I'm describing here. Okay, why can this be useful? I mean, the data are there in any case, so why not use them? And you know, if you manage to really capture the prior information, that should give you better results in terms of your posterior. Okay. Another reason why this might be interesting, and I'm going to show this to you on the MNIST example, is that the true dimension of the data, it's much less than the dimension that you're presented with. Okay. So for example, you might have an image that has dimension 10,000, but let's say the true dimension of that image is like 1,000. Okay. I'll try to be a bit more concrete what I mean about that in a second. But that basically means that you have you could potentially have a significant dimension reduction, okay? And obviously when it comes to sampling, or even when it comes to optimization, but even more when it comes to sampling, it's better to work in lower dimension in terms of computational efficiency than high dimension, okay? So this reduction can help you with sampling. So the way we're gonna do this, and that's, it's not a very complicated way, but when you see it for the first time, it seems a bit like black magic, and I'm afraid that I won't be able to describe it in the time that I have in more detail. But as I said, we're gonna make the hypothesis that the true dimension of data M lives in a much lower dimensional space, okay, than the original dimensional space. So I mean, the probabilistic way of saying that is, there is a latent variable Z that lives in a lower dimensional space, okay? And basically, there is a posterior, having observed Z, that sort of like takes me to my sample X, okay? So what the variation autoencoders are doing, they're trying to learn two functions, okay? An encoder, which is like a function in principle that takes you from X to Z, okay? So if you have X, what was sort of like the Z that gave rise to this X, and they try to do that in a probabilistic way, okay? So we assume that there's a probability distribution there, and a decoder that tells you, given Z, what X are you getting? And these functions are expressed as neural networks, okay? What do I mean by that in some sense is that they have a parametric form. So this phi and theta, you can think of them as being the parameters in your neural network, because that gives you a very sort of like flexible way of writing down this probability distributions. And you need to learn those parameters, okay? And how do you do that? You try to maximize the marginal likelihood of the observed data while ensuring that that the encoder is quite close to the true posterior. Okay, so I know that there is too much to take in. I'll have a few videos that try to explain this a bit more in a specific example. Okay. So going back to the point of sort of like reducing the dimensionality, X, remember, is in a high dimension, Y, Z is in a lower dimension. So if we're just to look at a simple denoising problem, so I've taken the matrix A to be identity, okay, and using the decoding network, we can write down basically the posterior on the latent space, okay. So the prior now is Gaussian, okay, and that's sort of like I have assumed that this pi of Z is Gaussian, okay, but now I have a non-linear likelihood, okay. So but basically this, so I went from a convex problem in very high dimension to a problem that is potentially non-convex but lives in a lower dimension, okay. And how much lower is this lower dimension? I will show you specifically in one example, okay. So the example that I'm interested in is the example of MNIST. So I have handwritten digits, okay, and I would like essentially, I mean, to learn the probability distribution that generates these images. First, I have to estimate the dimension, I mean, of M, okay, and it turns out that, I mean, these are 28 by 28 images, so you almost have like 900 dimensions. But it turns out, I mean, I won't go into much detail here, that you can estimate the effective dimension of this data set to be around 12, okay? So you have a 12-dimensional Gaussian, okay? You have learned your mappings from the space of Z to the space of X, okay? So you go from 12 dimensions to 900 dimensions using your neural networks. So let's do the following experiment, which is actually quite of nice and kind of cool, and that's sort of like partially the reason why people are using VAE. So I can generate a 12-dimensional Gaussian, a standard Gaussian. That's my Z, that's my latent variable. I will push it forward through my neural network, and this is basically going to give me an image on the space of X. And this is basically what you see here. These are some original data, okay, and these are some new data generated by this procedure. So as you can see, this construction that I told you has done quite a good job in terms of sort of like learning the probability distribution of the images here. Okay. So I have 3 videos here that I would like to show you. So the first one relates with samples from the prior distribution, just to explain a bit more what you were seeing before. So now I'm just reducing my distribution. I assume that the dimensionality is not 12, it's 2, just to be able to visualize things. And I'm just gonna be sampling from this Gaussian and tell you how the image look on the X space, okay? And this is just a video that shows different samples of the Gaussian and what are the corresponding images on the X space, okay? So as you see, as I move around, I get different images. I mean, the quality is not that great because I'm only using essentially 2 dimensions to describe a 900 dimensional image. But I hope it makes sense what I'm saying, that we have managed to learn the prior. So in principle, we could generate more images of our data set by using this procedure. Okay. But the problem is, in some sense, and this is sort of like what the next video is about, we took a convex problem and now we have turned it to a non-convex. So what this might create, it might create the following situation, okay? It might create situations in which you get stuck. So the mass of the true posterior is here, most of the mass of the true posterior is here, but somehow you manage to get stuck here. So what we've done, and again, I won't have too much time to talk about, we use something called parallel tempering, okay, and that allows you to basically get unstuck, okay? So we go back to where the posterior distribution has most of the mass. And again, I'm just showing you things in 2 dimensions for visualization purposes, okay? And it turns out that the most probable thing was this 6, and indeed I started with a 6 in which I added some noise. So it's good that my posterior distribution gives me that. Okay, I will just finish by showing you this comparison. Okay, so this was the original image. This was the image Y, if you like. Okay, and this is the comparison between what I obtain by using this data-driven approach and what I obtained using this functional prior denoise approach. And as you can see, the data-driven prior is doing a much better job in terms of denoising the image. Okay, it actually looks quite close to the original image. So just to conclude here, in order to be on time, and I apologize that I went a bit faster in the last part of the talk. So in terms of functional priors, I hope that I convinced you that using stochastic stabilized methods can deal with stiffness arising from regularization, and eventually and allow you to take larger effective time steps, which lead to rapid decorrelation. But also, as we've seen in practical examples, we have smaller bias. In terms of data-driven priors, we can reduce the dimensionality of the data. This comes with the price of losing low concavity. And then you would need to use Monte Carlo methods that they are not naive, because naive Monte Carlo methods might get stuck. And as I said, results suggest that the data-driven approach improves on the functional one. There is some future work here. I mean, I think actually Savas is going to talk about the first bit. And I would just like to thank you for your attention. And if you have any questions, I would be very happy to hear them. Thank you.
Excellent. Thank you so much, Costa. Let's see. Actually, I think I can allow everyone to unmute themselves. Now, everybody can unmute themselves. I'll give you a few seconds, and then we can all give a round of applause. Okay. 1, 2, 3.
Thank you.
Right. Very good. All right. So any questions? Yes, we already have one. So Costa Ocean is saying, how do you know you've chosen the right variational encoder architecture? The process of designing a neural network has always seemed rather arbitrary to me. So well, it says that, the rest of the presentation is more rigorous. So how do you design this architecture?
So, I mean, I personally didn't design anything. That's why it's good to have a smart PhD students. Okay. So I mean, there is quite a lot of literature out there and quite a lot of code that will do this for you in the in simple cases. So in terms of data set, MNIST is not a very complicated data set. Yeah. So I mean, I think when it came to that data set, Matt just basically took what was out there and just run it. But I think it's a very good question, but I'm afraid I'm not an expert in that part, so I cannot give you a straight answer. I think as with a lot of things of machine learning, there's a lot of sort of like trial and error, yeah, that you need to do. But I didn't do any of those things, so I cannot comment more on that.
Any other questions from the audience? Okay, people are thinking, and I have many.
Yeah, okay.
As usual. All right. Okay. So, okay. So I have another question. Actually, Ocean is saying, you wouldn't be able to know if you get stuck in the lower dimensional space there.
So to answer the question, can you?
Right. So
you can unmute him and he can ask you.
Yes, sure. I'm not sure.
Easier.
Right. So I'm gonna do that. I'm not exactly sure what he means here. Ocean, I think you can.
Hello.
Hello.
Hi, can you hear me?
Yeah.
Sorry. Just in the presentation, so when you compressed it down to two-dimensional or multi-dimensional, like countable number of dimensional space.
Yeah, you mean in the video? Yeah, here.
Yeah, in the video. So when you have sampled the entire space, you would know when you get stuck. But then in reality, you probably wouldn't sample the entire space, so you wouldn't know when you do get stuck, right?
Yeah.
Okay. So that could be that would be dangerous, just if you get stuck in the local minimum, but no one knows it. Yeah.
So I mean that is true. I mean that's always the problem in some sense when you go from something. So that's why, if you like, people have stuck with this sort of like convex models for a while. Yeah. Because there, sort of like that there is like only one maximizer of the probability, and you just go around. I mean, once the problem becomes non-convex, it becomes more complicated, and that's basically what we observe here. I mean, you wouldn't know for sure, but there is a number of like convergence diagnostics that you can try to do, basically to help you. But yeah, I mean, I agree. In principle, you wouldn't know. You wouldn't know that you got stuck. On the other hand, in this particular example, you wouldn't necessarily need to look at you wouldn't necessarily need to look even at the graph on the left. Yeah, I mean, this is an imaging problem. Yeah, I got a 6. I added noise to it. I mean, if it's telling me that the most, that the mean is a 7, then I would start wondering if there is something wrong with either with my code or with my prior. Yeah. So in this particular case, okay, even if you were not able to see the picture on the left, you would still kind of gauge that there's something wrong happening with either with your algorithm or with your prior. I mean, it could. The real question is, and I mean, Matt is kind of been struggling with that for the last year. So we are now trying to scale this to like more like higher dimensions and things like that. And I mean, it is a challenge from the computational point of view, but I mean, in my opinion, it's also a challenge from if you like, indeed truly learning the prior. Yeah. So they're like we try to apply these things, these kind of ideas on faces. Yeah. And you have like big data sets called like the celeb data set. Yeah. And you sort of like you use your VAE, you learn stuff, and then you have an image of you and me, and you add some noise, and then you try to follow this approach. And then, I mean, the prior is not really a prior for anything else outside the image of celebrities. If anything, you put my image and it start converting me to a celebrity. So, yeah, it's, I mean, the question is how much you can sort of like use like these things generalize outside of the things that they have been trained, if you see like what I'm trying to say. So
there's no way to measure that.
Yeah. But when I start looking like a celebrity, you know that there's a bit of an issue. Yeah. So yeah.
At least you look like human, even if you
yeah.
look
Okay.
like
Yeah.
a
Yeah.
celebrity.
We stay in the class of humans, but yeah. So
yeah.
Yeah, I think that's that could be a valid criticism of those things. But I mean, the idea in some sense is kind of universal. Then it boils down to sort of like, okay, how are you gonna try to learn this prior distribution?
Yeah. Okay. Yeah. Thank you.
No worries.
Okay. So thank you very much. Any other questions? Okay, I'll ask one while people are thinking. So Costa, you were talking about it being a challenge to sample in IID fashion from the final distribution, right? So you have a Markov chain, it's ergodic, you convert to some stationary distribution. What does it have to do with, like, it feels to me like the sampling step at the very end should be disconnected from everything else and the evolution, right? So what is the challenge there? It sounds like an honest sampling challenge.
Well, I mean, what I mean by IID, I mean, so this estimator that this integral that I've written down, yeah, okay. Once you are, once you are a stationarity, okay, still how fast samples decorrelate matter in terms of the asymptotic variance.
Okay.
Okay, because okay, you could still be at equilibrium, yeah, but move around very slowly, and that basically is not going to give you a big asymptotic variance for your estimator.
I see.
So even when you reach equilibrium, you still like to be able to. I mean, you should think of it in the context of I guess of this image here. Yeah, so you reach like the typical set. Okay, this is where most of the posterior is concentrated, but you still want to be able to move around quickly, because that allows you to visit more of the typical set, and that leads to sort of like small asymptotic variance.
I see. Okay, thank you.